curious about the physics of this model. I mean, okay,
yeah,
fine,
so
the equation is fine, but like,
so this model is so it's a Hamiltonian that's time dependent, right? And so this part is just sort of Hamiltonian evolution under some chaotic time periodic Hamiltonian. Okay. What's this? Well, this is sort of every site is coupled weakly to a back, and this is the coupling rate. The back is Markovian, and so this specific form of coupling, which is not important for my purposes, but it's some form of coupling, takes an up to a down at some rate. So it's like some kind of particle decay.
Yeah, but is it motivated by like actual physical system?
Yeah, I mean, you can have systems like this. I mean, it's motivated. In this case, it's meant to be so the point I want to make, I'm talking about systems that are geometrically local, but otherwise pretty structureless, right? So that's why I'm not telling you what the Hamiltonian is. But this form of system back coupling is fairly standard, but I mean, it's also not like, the only thing that's important for me is the system back coupling should be local, it should happen everywhere in space, and the batch should be Markovian. There's some instance of that general class of models.
And it preserves total spin.
No, it doesn't.
It doesn't preserve.
Yeah, no, it's because, I mean, this does, well, this doesn't even, because like this takes ups and downs. And the Hamiltonian right now is a Hamiltonian that does not have a U1. So right now I'm doing the case with no conservation laws. Yeah. So it's not, yeah, that's why the nature of that operator is not important, because Hamiltonian is so kind of like structureless that any operator is the same as any other operator.
Can you also explain the plot, please?
Yes. So there are two plots here, right? So there's the red plot and the black plot. Yeah. So the black plot is if I set gamma to 0 at the outset and talked about a finite system. Okay. So in that case, the spectrum of this. So in that case, this object that I'm talking about is a spectrum of a unitary evolution operator. The eigenvalues of a unitary operator are pure phases. Yeah. So spectrum in this case is sort of it's differences of phases. So sort of n squared differences of phases, and so that gives you this sort of this set of points that lie on the unit circle. Okay. Now I turn on the dissipation, and this is sort of physical disparate dynamics. So it takes you to some steady state, and you know, for the steady state, you are trying to not have any blow-up instabilities. Everything has to lie inside the unit disk, because that corresponds to modes that in discrete time contract. Yeah. So if you're used to thinking about this in continuous time, imagine Jerry graphically projecting, and then like these guys live in the sort of you know, left half plane or whatever.
Or his lower half plane.
Yes. Yeah, that's right. So whichever way you like it. Okay, so that's what this is, and so this is what happens when you keep the gap when you turn on the dissipation, keep the dissipation order 1. Now the question is, what happens when you take the structure, take the thermodynamic limit, and then take the dissipation to 0. And that's the thing that I think you know, I really got interested in because of the paper by Takashi Mori a couple of years ago, where what he did was he actually looked at this limit, and you can see that if you do the extrapolation from his numerics of what the gap is, you can see that the gap seems to extrapolate to a non-zero value even as you take gamma to 0, if you take the thermodynamic limit first. Okay, so that's numerical observation. You may or may not find this convincing. I mean, I probably wouldn't if it were just numerics, but he also had sort of nice arguments for it. But before I get there, let me just tell you the sort of story of like you know, that Mori told about like about how this phenomenon makes sense in the zero dissipation limit. So the idea is, you know, you have this set of poles, and if you take the thermodynamic limit, these poles merge into branch cut. You look at the resolvent of the evolution operator, you sort of push it through the branch cut, you emerge into a second Riemann sheet, and in the second Riemann sheet, for some models, not the model I was showing you, but some classical models back in the day, Ruelle found that you have these poles inside the unit circle, and these correspond to distributive modes. And so the idea is that this phenomenon could be some kind of quantum relative of these physics. Okay, but Mori had a nice argument for where these modes come from, and so remember that if you're trying to solve for the spectrum of one of these open system evolutions, they're not Hermitian. The channel is not a Hermitian operator, so you can think about either the left or the right action of the channel, and these in general will have different properties, and you know, they have the same eigenvalues, but the eigenvectors are pretty different. And so Mori's insight was actually a good idea to think about the left action of the channel. Why is that? Because the left action has this thing called the unital property, which is that it's like the physical Heisenberg picture. If you take if you take the identity operator and you evolve it, the Heisenberg picture remains the identity operator. This is true for a distributive system acting from the left, but it's not necessarily true acting from the right. But if you act from the left, then what you can do is you can think about the left eigenvectors in terms of operator growth in open systems. And so he had an argument based on operator growth that says that it goes like this, and I'll say this I'll say it slightly more precisely in a bit. But the idea is that operators that are very big decay much faster because they have a much bigger surface area of contact with the bath. And so under time evolution, there are two things that happen. Small operators grow big, and big operators decay fast. And so as you take the dissipation rate to 0, the eigenmodes, the eigenoperators get bigger and bigger, and that increasing size precisely balances out the decreasing decay rate per site. And so that was his argument. I'll sort of make it a bit cleaner than it was in his paper in a slide or two. So this argument gives you a gap in a channel, but you know, if you have a gap, then there's something a bit surprising, because one is used to thinking about gaps of a quantum channel. You know, eigenvalues living inside the unit disk is telling you there's some characteristic decay rate, and if this characteristic decay rate remains order 1, as you take the dissipation to 0, well, you know, how does all this structure of the OTOC and everything else show up? Because those things are also generated by the same quantum channel, right? So how do these two things fit together? Right. So what I want to do quickly is talk about how this all fits together. Now, once you realize that the problem you're trying to do is dealing with operator growth and presence dissipation, there's this rather nice picture of what's happening. So you can think about operators in some coarse-grained way as governed by their size. You know, and so as time passes in a unitary system, small operators get bigger and bigger, and the way they get bigger is they undergo a bias-random walk towards becoming more complex and bigger. Right. So this is a strict Markov process for certain circuit models, but it's believed to be essentially correct very generally for chaotic dynamics. Now, what the dissipation does to add to this Markov process, which is a bias-random walk, is it also adds this feature that operators decay at a rate that's proportional to how big they are. So that gives you this additional feature over here. And so what we want to do now is, instead of thinking about the complicated problem of you know, an actual operator, an actual system, we just want to think about the structure of eigenmodes of this simple Markov process. Well, it's not really a Markov process once you put this in, but it's like some simple non-Hermitian operator which you can then diagonalize. And so when you do that, one thing you realize kind of quickly is that there is a similarity transform that's going to take this Markov process and turn it into a Hermitian matrix. And in the continuum approximation, this Hermitian matrix looks like just a Laplacian with a potential that's linear in position. Okay, so we know how to deal with this. Like, this is sort of area functions and the like. Yeah. So this, and the interesting thing about this coordinate transformation is that it actually introduces a gap. So when you go from up here to down here, that transformation sort of introduces this gap, which is going to be the gap that remains in the gamma to 0 limit. so that's how this works. And I'm not going to talk about this in detail, but in fact, the behavior at very small operator size is non-universal, and you can also have, in addition to this overall area potential, some kind of local structure that puts a bound state inside near the origin. So that in principle that could give rise to a sort of a phase transition where the bound state is either there or not there, and it has a threshold for arising. You had a question?
What do you mean by the gap is introduced by the coordinate?
Well, so if you perform this transformation, right? So I have this equation, right? And so when I transform it, it looks like this. So there's this constant piece that shows up as part of the transformation, and that's where the gap comes from.
If gamma were zero from the beginning, then somehow transformation would have to be different, right? Because the limits are.
So what happens is that when gamma is zero from the beginning, then this is actually still okay. But these eigenmodes stop being normalized. That's what goes wrong in that limit. Yeah, everything else looks very similar, and this gap. Yes, the gap remains. The gap doesn't really care about gamma, but the eigenmodes stop really existing as well-defined eigenmodes. That's what goes wrong.
So what I did to that very first equation, because why is it linear in rho and why is it so local in time? Because in general you will have nonlinear terms in rho, and you can also have it can be a very non-local equation both in time and space.
Yeah, so this is basically our coarse-grained understanding of operator growth. So in a chaotic system, small operators grow bigger at some deterministic rate. And so this is basically making, if you like, in general it's going to be an approximation, at least when the operators are small, that this process is strictly Markovian. Right, so in general this is going to be slightly non-local in time, but once the operators get big, there's sort of a huge entropy of big operators. So it's believed to be sort of a good assumption to say that when the growth of a typical operator of size n to a typical operator of size n plus 1 is just described by some kind of rate equation, because there's no coherence left to those very clear schemes.
So gamma is entering in other places also besides that last term?
No, gamma. Sorry. Okay. So yeah. So I think so. Imagine. So forget it. Yeah. So I screwed up by combining things from too many slides. But yeah. So there are gammas in this figure that are irrelevant. So the actual equation is the thing that I wrote over there, right? So gamma is the dissipation, and it only shows up in the fact that big operators die out faster. The bigger they are. So that's where gamma shows up in the operator growth.
Sorry. So if you don't do the rotation, how does the eigenspectrum look of the non-Hermitian matrix?
I'll come back to that, because I'll do the rotation, solve the problem, and rotate back. Okay. I'll get there. All right. Okay. So that's this summation problem. So you can solve this thing in terms of various functions, and then you can rotate back the solution. And the thing you realize is the Hermitian problem, of course, has orthogonal eigenvectors. But when you rotate them back, they sort of become, because the similarity transformation is so non-unitary, they become increasingly non-orthogonal, and so in fact all of them are sort of massively peaked at size 1 over gamma. Okay, because that's what the transformation did. And this is why, as you take gamma to 0, this problem becomes it's a very singular limit, because then these things are not normalizable even. For any finite gamma, they're well-defined. Okay, and so the fact that these eigenvectors are extremely non-orthogonal allows you to have decay rates that are not set by the gap, and in fact much slower than the gap. So the picture here, which some of you might recognize from having done non-Hermitian stuff in the past, is that if you take the eigenvectors of a typical non-Hermitian matrix with sort of a lot of very close to parallel eigenvectors, then if you try to expand a generic state in this eigenbasis, you need giant coefficients because these guys are sort of pointing almost orthogonal to the state you're trying to expand. And so this gives you these giant coefficients, and in fact these coefficients scale as 1 over gamma, as either 1 over gamma in this problem, and then now when you time evolve this thing, for these coefficients to all become small and for you to be dominated by the leading eigenvalues, you need this entire thing in the exponent to become small, and that allows you to have decay rates that go as in things like the OTOC that go as 1 over gamma. So it just comes from this.
So 1 over gamma, because in the limit gamma to 0, they should scale with 8 by space dimension.
Yeah, basically what happens is that these guys are all peaked at 1 over gamma, right? And they're actually this is a log plot. So if I take some kind of operator at the origin, and I try to expand it in terms of all of these guys, I'm picking up the exponential tails. And I need to sort of choose the phases very precisely to have all of these like big peaks cancel out. But as I time evolve, I dephase and I start developing the big peaks. Okay, so that's so operator growth doesn't tell you about these. Operator growth cares about this 1 over gamma, even though the spectrum, it's not in the spectrum. It's in the eigenvector correlations. This picture also tells you what's special about local correlation functions, because local correlation function is a return amplitude for a small operator start small and be small at the end. And if you look at the way this coordinate transformation works, it does almost nothing to small operators, right? Its effects increase exponentially as the operators acting on get bigger. And so you look at operators of size 1, you might as well be doing the Hermitian problem, and you do have the decay rate that comes from the Hermitian problems. None of this funny similarity transformation stuff really makes a difference. This is like saying, an analogous problem is if you think about a biased random walk, and you condition the probability distribution of the biased random walk on coming back to the origin, that conditional distribution is the same as the unbiased random walk. And so this is the same basic picture as that. If you're talking about return amplitudes, the bias of the random walk kind of falls out. Okay. Finally, let me say one thing about how all of these things fit together. So the picture overall that sets the eigenmode is that you have these operators of various sizes. The small ones are sort of the weight at small operators is decreasing because of operator growth. The weight at large operators is decreasing because of the system decaying into the path. And the eigenmode is basically set by balancing these two rates. So basically the bottleneck is the bottleneck of small operators getting bigger. And so the way the solution works is that the eigenmode gets big enough for the saddle point to match the rate which small operators get bigger. So operator growth indirectly, but quite generally sets the decay of local correlation functions, even though those seem like quite different phenomena. They're tightly related by this overall picture. The eigenmode's the non-Hermitian operator. Okay, so that's the summary of the stuff. So correlation functions are about operators that remain small at all times. The eigenmode consists of operators that get gigantic, and the OTOC at its peak is governed by some intermediate scales. So sort of many different scales that show up in the dynamics of various observables and non-observable, various types of objects in your theory as you take the dissipation rate to 0. Okay, so that's the summary of this part of the talk. So local channels remain gapped. This gap is set by intrinsic properties like the rate at which small operators become less small. And so I didn't talk about this so much, but you can get spectral transitions in the low noise limit, in the rate of, in how the gap changes with parameters of the system. Okay, so that's the first part of my talk, and so let me stop for questions about this before I move on to the case with the conservation law.
Sorry, very basic thing. So basically, you want to understand the dynamics without dissipation, right?
Yeah.
Then to understand some properties, one has to go through a case with dissipation. Is it what you are?
Yeah. So there are two things, right? We're interested in both the dynamics with dissipation and the dynamics without, and of course how they're connected to each other, right? And so the question is that as you take the dissipation rate to zero, some things behave singularly, like otarks or like certain more subtle spectral properties. Some things just behave in a very simple way, like correlation functions. Mm-hmm. And the question is, how do those, seeing as you have some linear map, how does it fit that some things are singular and some things are not from the properties of that linear map? And so the conclusion is that the spectrum of linear map has a gap, and it actually changes discontinuously between the low dissipation rate and zero dissipation rate. But as you go towards that limit, the map gets increasingly non-normal, and so a lot of long time scales emerge from the increasing non-normality of the map.
In the end, at least some part of the conclusion can be drawn by considering the system without dissipation.
Yeah, so I think you could get some of these things without the dissipation, but I think you wouldn't. The question about the eigenmode, for example, wouldn't be well defined, right? So yeah, so indeed you can get the fact that local correlation functions decay exponentially. That you can in principle do without dissipation, but secretly you're always putting in dissipation there in order to suppress Planck array recurrence. This is doing it more systematically. Yeah. Okay. So let's go from left to right, so I can keep track of. Ben, do you have a question?
Yeah, I had also I think related. So naive question. So your picture of the local correlation function with where x doesn't grow so much, right? Yeah. So essentially, the dissipation should not affect that too much, and so naively you would think dissipation zero limit is actually not singular. But is that the case? Because then you said that in non-dissipative system, Gaussian decay is not exponential; it's a stretch exponential. So it is singular.
Well, that's the conservation law. So I'll come there. So here that's not.
That's the conservation. Okay.
So I think when people talk about RP resonances, they usually look at the spectrum, the time evolution operator stuff. You're now looking at the spectrum, the transition matrix associated with the operator dynamics. And are they a priori related, or?
So I don't know of a simple mathematical way to connect them, but if you do the same thing of putting in weak dissipation and computing spectrum of the transition matrix, that also shows RP resonances in the classical problems where you see RP resonances otherwise, and the same resonances. So Gopalakrishnan has some papers about this, but I don't really understand. In this problem, I don't know how to do the problem the other way. This is the only way I know how to do it. So it's hard to match. Yeah.
So, if I understand you correctly, what you're saying is, so the correct way of taking my thermodynamic limit or so would be to take my system size to infinity without any dissipation, and now but the alternative way would be to introduce the gamma dissipation, do the infinite system limit, and then go. So when you have these infinite system limits, then there's this C-star algebra approach where you only study local observers.
Yeah.
Can you distinguish these two limits when you only study local observers?
Yeah, no, that's a good question. I think that if you talked about operator growth in, I don't know, maybe Kurt has some thoughts about this because he's the C-star algebra guy. I guess maybe Benjamin has. But if you think about operator growth, local operators sort of stop being local, right? That's how operator growth in a unitary system works. So I think at some level there might be dissipation even in the construction of some kind of closed evolution on the algebra of local operators. I think that's implicitly dissipative always, to be closed.
Since you talked about So in a classical setup, so if you have some classical, say a Hamiltonian or even non-Hamiltonian system, you could also in principle add noise and question, say, or talk, and then I think you were referring to the paper where they look at the Pessin relation. Maybe they look on the Kolmogorov entropy on the one side with noise, and find that indeed it reproduces in the small noise limit the Lyapunov of the isolated system. So in that case, there is no distance between. In that case, they can smoothly take the noise limit to 0. So I understand it's a regulator of the computation, but it.
Yeah, no, that's right. I think that in some cases this limit's going to be smooth, right? But in this example, for example, a chaotic many-body system, it's not smooth. And in some classical systems also that Ruelle studied, it's not smooth. I'm not making a claim that all dynamics has a singular limit. It's just true for chaotic many-body systems. John, did you?
Well, I think it was basically Takato's question. I mean, whether for the kind of problem you studied, you can go backwards from these eigenvalues that you were computing to the quantities that were the poles in Maury's picture in the complex plane that you started with.
Yeah, I'd leave that as an open question for now. Like, I don't know. I feel like it should be doable, but I'm actually kind of confused even in the classical setting as to how, these two. There's a calculation that Kochan does where he turns on dissipation, solves one of these problems, then takes the dissipation away. And there's another problem, there's another way that Ruelle does it, and they're totally different a priori, but they end up giving the same answers. They're connected deeply somehow, but I don't actually understand.
But the classical version might be much more difficult than.
Yeah, it could be that Yeah, so it's a good question. Like, what the action analytic properties of this resolvent are and how they behave as you take the weak dissipation limit. That's kind of interesting. One can talk about the pseudospectrum, and the pseudospectrum presumably does something fairly singular. But yeah, I leave that as an open question for now. All right.
Yeah. So maybe I missed your explanation, but so at some point you introduced evolution equation, differential equation for the density matrix, and then in the equation the gap naturally appears. Yeah, this one.
Oh yeah, so sorry, let me actually be clear here that so my notation is a bit unfortunate here because this is not the density matrix. This is, right, so what's happening here is that I'm taking operators.
Okay.
Right? And the operator, in the closed system, the operator has a preserved L2 norm. So I can break up the operator into pieces of various sizes. I can define a density of operators at a given size. And so that's what I mean by
distribution function.
It's a distribution function of the operator. It's not the density matrix. The density matrix doesn't have
Sorry, I missed. Yeah. Anyway, so my question is, so in that equation, this gap naturally appears, but in the introductory part, you mentioned this result by Mori that this gap passes in the limit of gamma goes to 0, but which is only the case when you take the thermodynamic limit first. So my question is this continuum limit, taking continuum limit here corresponds to taking the
it's actually, the thermodynamic limit corresponds to making this, it's not the continuum limit, it's taking this thing to the semi-infinite line.
Okay.
Right, because if you took a finite system, an operator could only get so big, and it occupies the whole system. That would correspond to putting a hard wall over here at some point. And then, of course, then when the hard wall is nearby and the slope is small, then it kind of doesn't matter. Then you end up with sort of a different problem.
I see. Okay. So it's not like a continuum limit, but taking a semi-infinite limit
semi-infinite line
corresponds to thermodynamic limit.
Yes, precisely. And it corresponds to that because operators can be arbitrarily big in thermodynamics.
So only in that limit this gap makes sense.
Yeah, exactly. Yeah.
Okay, thank you.
Yeah, otherwise the gap crosses over to something that's size dependent.
Thank you. Yeah.
All right. Now let me use the not very many minutes I have to talk about something a bit different, which is what happens when you take the same setup and try to think about introducing charge conservation. Just to remind you how this works. So once you introduce charge conservation, if you take a generic operator, the generic operator has correlation functions that are set by hydrodynamics, right? So going to decay its power laws. And so the way you do this for a generic operator is you look at it and you say, okay, is it allowed by symmetry to overlap with any of the designated slow modes, which are densities, the gradients and products of densities. And so for most operators, this overlap is allowed and therefore it forms at some order. But then you have operators like this. So if I have charge conservation, my evolution operator is block diagonal, and so I can think about an operator like, for example, the raising operator changes the charge on a particular site, and now that guy only has matrix elements in these blocks, and no matter how much you evolve it, it's going to remain off diagonal by the same amount. And so that means that it's not symmetry allowed to talk to any combination of charges, products, or derivatives of charges. So naively, it's not allowed to develop a hydrodynamic overlap. And so one simple guess might be that such operators don't develop hydrodynamic behaviors at all. They're not affected by the hydro. They should behave like the nice exponentially decaying guys that I talked about. In fact, Mori in his paper basically conjectures that and says, you know, you have these off-diagonal guys, and they just have Ruelle resonances. Okay, so now when you start thinking about this, you realize it's not actually so simple, and the basic mechanism by which something non-trivial can happen is the following. So if I consider taking a correlation function, and let's forget about the noise for now, let's just talk about the isolated system. I imagine taking a temporal correlation function in the isolated system. The isolated system is the infinite temperature state, or any finite temperature state, but it's an ensemble of all possible bit strings. And this ensemble includes a bunch of bit strings, they're very rare, but they're still present, where in the initial state, I had a big hole around a particular point, right? So there's no charges within like some distance x of my reference origin. And so these are exponentially rare, but they're present. And so I can divide my correlation function, I can divide my initial density matrix into stuff that into stuff that has the void and stuff that doesn't have the void. And I can say my correlation function is a sum of two pieces. So here, this is in general an assumption, but it seems a reasonable assumption. You cannot really have cancellations between these two pieces because they're chosen in sort of totally independent ways. And so if this piece decays sub-exponentially, you would expect the full thing to decay sub-exponentially because there's no mechanism for it to be cancelled out by the typical regions. And so we're going to focus on the contributions, the correlation function due to these rare regions in the initial state. Okay. Fine. And so now the key thing is to ask, well, what happens when you start an operator and the operator, is a perturbation of the initial state, but you perturb the initial state in a void.
Can you define again what's the void?
Yeah, a void is a region of size L. So I'm assuming that there exist sectors of the conserved charge that are zero entropy. Okay, and so that's in general for U1 charge as an assumption. But if you had energy conservation as well, then it's just the third law of thermodynamics. But in general, I'm going to treat that as an assumption. So you assume there are zero entropy states. And now what you do is you say, okay, a void of size L is a state that's arbitrary outside this region of size L, but in here, inside this region, it is the zero entropy state. That's what a void is. Okay, and so now if you make this assumption, then what happens is that, so the void looks locally, inserting an operator into the void is locally like doing a single particle problem, right? You have a vacuum inside this region, you insert a particle into the vacuum, it just moves around. It doesn't collide with anything until the void begins to fill in. And so we're going to make a pessimistic assumption that once this inserted operator, once the inserted quasi-particle hits any other quasi-particle at all, it just dies, it never comes back. That's a pessimistic assumption. You expect it to give you a lower order correlation than the true model would. But under this pessimistic assumption, you can think about the dynamics of an operator in terms of this like fairly simple dissipative single particle problem, where you put your quasi-particle into the void, and then it wanders about, and whenever it hits something else, it just decays. So that process is governed by a non-Hermitian Hamiltonian, and you're asking, if you like, about the propagation, the survival probability under this non-Hermitian Hamiltonian. Yeah.
I thought there was charge conservation.
There is, yeah.
So then these quasi-particles are not charged?
They are. They're so I'm thinking about something like a sea dagger. If you're thinking about charged fermions.
Then how are they dying?
Because what happens is that a sea dagger becomes, like, for example, a sea dagger C, which is allowed. And I'm saying that once it becomes a complex thing, it never comes back. Right? Because if sea dagger goes to sea dagger C, that's not going to contribute to the correlation function. To contribute to the correlation function, it has to come back to just being a sea dagger. Entropically, it's unlikely to do that once it starts colliding with stuff. And so the pessimistic assumption is that once it sees anything at all, it's just gone. It has no chance of ever coming back. So that's the picture. Okay? And remember, we're trying to, the fact that it's sub-exponential is the sort of non-trivial thing, right? So this is all these assumptions are in the direction of making it more exponential. Okay, so now that we have this picture, what we have to do is we have to think about what the propagator, what this propagation is, right? So you have this void, you have the stuff outside the void, and as time passes, this object, which is a density of background particles, evolves according to regular thermodynamics. According to regular hydrodynamics. And so we put that hydrodynamic evolution in, that gives you this time dependence, but that's sort of an external thing to this problem. And then you solve this one particle problem in the presence of that background, that hydrodynamically evolving background. And so there are two cases to think about. The simplest scenario is the case where the time evolution is kind of random in time. So in that case, even the particle you inserted into the void is just sort of bouncing around diffusively. In that case, it's fairly simple to see that because diffusion constant stays constant, you can just sort of integrate this equation. It's just a bunch of Gaussians, and if you work through the details, you'll see that the void that this particle you put in there doesn't really begin to decay until the void is basically totally filled in. And so the time scale in which it does that is L squared. It's just it's just set by the time it takes for things to diffuse into the middle of the void. But of course, now I ask what the correlation function does. I fix t. I ask how big a void do I have to create for the correlation function to live for a time t inside the void before it dies. Well, that's square root of t. And so the probability of creating such things goes to e to the minus square root of t, and therefore the correlation function, the survival probability of the correlation, also goes to e to the minus square root of t.
If I had a sort of non-random Hamiltonian, I'm a bit confused by this argument, because then I would have a quantum walk, not a...
Yeah, that's the next slide. Okay. This is the simpler case, where the hydro is completely transparent. But yes, in this case, you get e to the minus square root of t, right, by this sort of very simple reasoning.
So question about the simpler case. So here you should be summing over the different sizes of voids, or?
Well, I'm just saddle pointing the sum, right? Because I don't. If I had voids that are much smaller than this, then they would fill in at this time t, so it wouldn't be relevant. If I had voids that are much bigger, they're not buying me anything, and they're much rarer. So implicitly saddle pointed the sum. But yeah, now coming to Andy's question, what happens if the problem is translation invariant, and so in the low density region, you have ballistic motion rather than a random walk. So here the key thing is you've got to think about the way in which the void fills in, and that requires particles to come from the outside into the void, right? And so that's a process that's actually bottlenecked way outside in the region of typical diffusion constants, because particles have to move through that typical region in order to enter the void. You can solve this problem by studying basically the hydrodynamics of a diffusion equation with a diffusion constant that's singular in the density. The diffusion constant is 1 over n because each collision is completely randomizing. That's sort of a reasonable assumption. So the diffusion constant goes with 1 over n, and you ask, well, starting from this domain wall initial condition, what's the hydrodynamic solution at late times? You can solve that. It's a fairly simple solution. What you find at the end of the day is that the density at the middle of the void scales as T over L squared if the void initially had size L. Okay? So that just comes out of solving this sort of density-dependent diffusion equation. And so now what you can do given this behavior is you can say, okay, so now I can ask, well, I ask if I inserted my operator in the middle of the void, how long does it take to, what's its decay rate at time t? Its decay rate at time t is T over L squared. You plug in, so the contribution of the correlator from void to size L has this piece that's given by the rareness of the void, and this piece that's given by the decay rate for a void of that size. You optimize this by saddle point, and you find that the saddle point solution gives you a correlation function that decays as e to the minus t to the 2/3. And this actually works quite well numerically for a number of different flow-K models we looked at, so it seems to check out in general. So yeah, the key thing is that even if inside the void things are able to move really fast, the rate at which things sort of enter the void is still bottlenecked by the fact that the current far away from the void is diffusive.
So, but basically you're saying that the correct hydrodynamic equation is that diffusion equation with the 1 over n.
Yeah, exactly, yeah.
Which is just telling you that as you decrease density, you just become more and more ballistic.
Yeah, exactly.
I feel like maybe the way I would can I alternatively think of this because I'm a bit sort of, I don't know, I'm not sure I totally buy the sort of H effective with the imaginary part. But can I think of it as like I have a Gaussian in the middle?
Yeah.
Like in early times I have a sort of sharply peaked wave function for my single C dagger, if you will. It's quantum walking, but and so like most of the operator does hit the wall.
Exactly. But there's a polynomially small fraction.
But you have a 1 over square root t sort of from the small momentum mode.
That's right. Yeah, that's right. So there's a big part of it that's got a low group velocity, and that's only a polynomially small part of it. And that polynomial, so there's 1 over this e to the minus whatever is multiplied by a polynomially small factor. We're not keeping track of that from the survival probability of the quantum walk. Yeah, that's also a perfectly fine way of thinking about it. All right. So I'm pretty much done. I had just one more key thing to say, which is that the moment you put in noise, this entire structure breaks down. The reason it breaks down is that this thing that I was talking about was, if you like, the size of the correlation function, right? But the correlation function is also picking up, because it's a charged operator, it's picking up phases as it evolves. It's not just it's not staying. It's oscillating wildly. It's oscillating wildly in a way that if you average it over a big time window, it's actually gonna decay exponentially. So it's like the phase structure is important, and the moment you put in noise, you're basically averaging out the phase structure, and then you get regular dephasing, and the correlation function decays exponentially in time. So that bit, and then the crossover between the coherent and incoherent regimes of weak noise that goes as t to the minus 1/3, and if you're outside of that, if your time's longer than that at finite noise, just cross over it exponentially.
But is the noise here like symmetry breaking?
Yeah. No, it's symmetry. It's strongly symmetric. So it's U1 preserving symmetry. So even if the noise preserves the symmetry, it still doesn't. It still causes, if you like, you're averaging. It's like you take this overall envelope, but the envelope also has a bunch of oscillations in it, and the noise messes up the oscillation structure and averages over it, and so it sort of makes the noise average correlator actually decays exponentially. So this effect is coherent in a sense. It sort of depends on the coherence inside the void. Another way to see this is that that extrinsic noise violates the zero entropy condition. So you wouldn't expect it to work. Okay, I don't have time to talk about this, which is good because I don't want to. But so you can say all the stuff less intuitively and more precisely. In the case of random circuits, we can do the averages over certain ensembles and so on. Okay, so that's pretty much what I wanted to say, and I want to end on time, so I'll just leave this up and take questions if there's still more questions.
So the kind of observables that you're looking at is like correlation function, something like C dagger and then C attempt T. And why do you say that there's like no, I don't understand. Like my understanding of this would be like, you know, you have the equilibrium state, now you after C dagger, you create like some particle, and then like this particle now evolves according to hydrodynamics or something like this, and then you destroy it at some later point.
The key thing is the particle lives only on the ket and not the bra, or only the bra and not the ket, right? You're creating a state that's sort of that's off diagonal in a sense, right? You're creating your it's not like you're putting in a particle, because that'd be putting a C dagger both. It'd be acting a C dagger to the right and acting a C to the left. That's what the operation of creating a particle is. Here you're creating a superposition between an n+1 particle state and an n particle state, and you're looking at the evolution of that superposition.
But it's like so if my initial state only would be a microcanonical ensemble in like one of these sectors.
Yeah.
Then like what you would do is you would add another particle into it.
No, you wouldn't, because that would be acting on both the bra and the ket. You'd do a superposition to measure this thing experimentally, for example, directly. What you would do is you'd create a superposition of like not having a particle and having an extra particle. And you'd be looking at the off-diagonal piece of that superposition. That's what non-hydrodynamic correlation is. It's not putting a particle in. Putting a particle in is creating a state with an extra particle, and that's acting on both the bra and the ket. This is only acting on one side.
So I'm confused about how noise didn't matter for the like in the case with conservation laws, because.
Wait, in the case without, right? In the case where noise does matter.
You said instability against noise, so yeah, okay. So noise matters here. No, but then can't you think of like a random circuit averaged over noise as being some kind of a dissipative?
Yeah, that's right. The random circuit average over noise is not going to have this feature, right? So the thing that has this feature in the random circuit case is look at where the squares and the averages go. So you're measuring correlation function, you're squaring it, and then you're averaging over noise. If you averaged over noise before squaring it, it would not work. You would get something else.
Would be two questions. First, I mean, you said that if you time average, then you recover exponential decay. So is it a general expectation that actually when you time average local observables, then everything is normally behaved?
I don't know. I mean, it's a good question.
So that's a good question. What about in higher D, you said here in 1D?
Yeah, that's right. So in higher D, this argument doesn't quite give you the same thing, right? In 2 dimensions, it's marginal because the contribution from voids is exponential, and so is the probability of having voids. So in that case, we don't quite know what's going to happen. That requires more careful analysis. And dimensions higher than 2, the void effect is subleading. Because, for example, in 3 dimensions, there'd be the probability of creating a void that survives for long enough is going to be e to the minus t to the 3 halves, which is subleading to exponential. So this effect is like quite specific to 1 dimension because it just takes a lot longer for voids to fill in. If I had fractons or some other kind of slower dynamics than diffusive, then the critical dimension would move around. So fractons in 2 dimensions would have the same effect.
Fractons in the void.
Yes, if I had a charge and dipole conservation, and I asked the correlation function of a non-hydro operator there, then that would be by the same argument here.
You need the void dynamics to be fractonic.
Yeah, you need the dynamics to be fractonic everywhere. Yeah, that's right. If your base model was fractonic, then this effect would persist to higher dimensions.
But somehow in that case, I would expect that it's, because like the single particle excitation would then be completely frozen.
Yeah, then it might be even more stuck. Yeah, so in that case, you might actually. So if you had, so I'm not actually completely sure. Are there fracton models with like that at low density have a Bloch theorem for dipoles? I guess there must be, right? So if you wrote down Hamiltonians, in that case, I think this argument wouldn't change so much because the quantum walk wouldn't go anywhere. But like we're really just looking at the part of the quantum walk that morally didn't go anywhere anyway. So you'd probably still get the same argument of just it sticks around until dipoles come ballistically in and then start colliding with it. Yeah, that depends a bit on details. It might modify things in the direction of making them even